Hello, class. I I had started to do this lecture, and then I realized that I had gotten d theta, or theta. I'd put that off the xy, and anyway, I thought I'd just redo it again. I want to point that out, though, that even in the last lecture, when I was sort of introducing the spherical coordinate system, I mentioned that phi, of course, is an angle that is off the positive x-axis. But I think I mentioned in the last lecture that theta was the angle that was rotated off the positive x-axis toward the radius, the r, and it's not. Theta is off the positive z-axis. So those are our two references. Phi is always off the positive x-axis, and z is always positive off the positive z-axis, okay? And so it still is true that theta only goes 180 degrees, phi goes 200 or 360 degrees. I don't know, just too many things on my mind at once. So if I look at this, the whole thing, first of all, for the spherical coordinate system, let's just look at a point in space. And in fact, what I want to do is I want to look at that differentially small element. Let me just draw that here. That's the differentially small element that I'm talking about, right? That differentially small element right there. And then what I did was I blew that element up over here so that we could see it better and we could actually come up with the lengths of each of the individual sides of that differential volume element. Not only that, I also wanted to see, what the differential surface areas were. The surface area here on the front, and then the surface area on the side, and also, just like I did with Cartesian and cylindrical coordinate systems, and also on the bottom. And I want to go over that again, because when I was doing this is all right, by the way, but I switched this around, and I'm going through the transformations down here. So I'd like it to be correct anyway. This is going for posterity. So let's just look at this. Actually, I drew this so well, didn't I? If I look at a small little differential amount of d theta. Now, when I'm saying that, looking at a differential amount of d phi, did I say theta? Of d phi, it's just going to be right here, right? Because we've got this angle right here is d phi. And so if I have d phi, and we all know from before that if I have an arc subtended by a radius like this through that angle, that S is just going to be equal to R times theta, right? Let me just sort of cut that out here. And so we know that this out here, since this is a distance R away, and it subtends an angle of d phi, that the length of that arc has to be r d phi, right? Now, when I look at theta, as theta is coming, down in this direction, I can see that theta, this angle right here, right? Again, we're just using this identity, is that I now have an angle that is d theta, that is, or subtends d theta, r, this is still r, this is still r, and then this little bit here is dr, right? So if we look at this small, infinitesimally small volume, we see that this side here is dr, This side here is r d phi, but then r d phi, if you look at how this goes up to 0, I've got r d phi, and then how is r d phi changing, right? So we know that if it starts out at 0, right, because this is when theta equals 0. So at the z-axis, theta equals 0 degrees. And then down here at the xy plane, since theta is increasing as it moves away from the z-axis, down here it'd be 90 degrees. So in the xy plane, theta equals 90 degrees. Well, now what at 0 is 0, and what at 90 degrees is 1? Let's see. 0 degrees, it's 0, and 90 degrees, it equals 1. I think everybody can see that that's the sine function, isn't it? And so I've got r d theta, so up here, r d theta times the sine of, r d phi times the sine of theta. So the sine of theta at 0 is 0. The sine of theta at 90 degrees is 1. So I've got r d phi times the sine of theta for this small side down here, right? So dr, that's just the extension of r, and then r d theta, because that right there, if this angle is d theta and r, subtends d theta, then the arc that we're going to get there is r d theta. So we have all of those individual sides now. We've got a cube here. We'll say that that cube is cubic, right? And we've got dr, r d theta, r d phi sine theta as the lengths of the three sides of that. So when we want to look at the front side, what do we have? We have r d theta times r d phi sine theta. I've got that written out here as the first one. Well, I think everybody can see that we've got r times r, that's r squared. Then we've got d phi, d theta, and then we've got sine theta. So to define this side right here, this front side, this differentially small surface area is going to be this. Now, you're probably thinking, well, what if I took that then, that differentially small surface area, and then I integrated over all of those angles? Would that end up giving me 4 pi r squared? Yes, it will. Absolutely. Anyway, now let's keep going. Now let's look at the side. This would be the side over here. We see one side is dr, and we see the other side is going to be r d theta. So r times dr times d theta. And how about the top? Whether it's the top or whether it's the bottom, we still have one of the sides is r d phi sine theta, and the other side is dr. So I've got r dr d phi sine theta. Does everyone understand, how that works? Now, the last one that I wanted to do was the differential volume area, right? The differential volume area that we have here. Well, we have all three of the sides now, so let's just multiply them all together. So we've got r d phi sine theta times r d theta times dr. So r, those appear twice, so that's r squared times dr, let's put those close to each other, times d phi times d theta times sine of theta. So our differential volume here is not dx times dy times dz like it is in the Cartesian coordinate system, is it? No. Here, what we have is a volume area that looks a little more Well, let's just say it's not dr d theta, is it? So we have to look at that when we start to work with these. Now, if we've got these differential volumes, we're probably thinking, well, we're going to use this for integration later on. And that's right, we are. You know, I want to point out a couple things. First of all, I forgot to finish that one equation down there because I got off on a tangent talking about inverse tangent not being cotangent. And that's what I want to do here too, because we've got the Cartesian cylindrical coordinate transformation. These are transformations between the two different coordinate systems that I've got mentioned in each one of these boxes. So for Cartesian to cylindrical coordinate systems, the z is exactly the same, right? So we don't have to worry about that. We only have to worry about what's happening in the xy plane. So what is happening in the xy plane is really just like going from phasor notation to a plus jb complex number notation. And so we know rho, or as in your book, small r, is just going to be the square root of x squared plus y squared. And we know that the angle is just going to be the inverse tangent. And that's why I started talking about cotangent in this. People before, and you want to point that out too, to anybody that you're teaching or supervising or whatever, tangent to the -1 is not 1 over tangent y over x. No, not at all, right? It's not a reciprocal. It's an inverse. That -1 stands for inverse function of tangent. Cotangent would be tangent to the, would be 1 over tangent. So the cotangent is 1 over tangent, but the inverse tangent is not the same as 1 over tangent of A. I probably should have picked a different variable there, but whatever. Okay, so here's our transformations then. Cartesian to cylindrical, pretty straightforward. Cylindrical to Cartesian, pretty straightforward because they share the z-axis, right? So we've got r times sine phi, r times cosine phi, and that would all be fine. Now, if this is theta and I'm coming down there, then let's look at a couple distances here. Well, if that's theta that's rotating out to that point, right? Then if I was to drop this down onto here, this, you can see that's theta, but then wouldn't this also be theta, right? Parallel lines. So that would be theta, and that is theta. So that distance coming down there is theta, and then this distance on the other side, this being a right triangle right here, if that's theta, then this side has to be r sine theta, doesn't it? Does everyone see that? R sine theta. And then if I was to drop a profile from this to the x-axis, and I've done that right there, if I was to drop a profile of that to the x-axis right there, what would this distance be? Let's call that distance x. So x equals r sine theta, right? That's just what I've got there. That's the projection of r, right? R is just a distance, and I'm projecting that down onto the xy axis. And I know that this angle here is theta, so I know this length right here has to be r sine theta. And then if I take r sine theta, and by that distance right there, I mean this distance right here, right? That's r sine theta. So if I take r sine theta, this distance right here, and I project it down onto the x-axis, I get r sine theta times the cosine of phi. right? Because phi is positive off the x-axis. This is phi right here. So x equals r sine theta cosine phi. Now y would be the same thing, r sine, but now instead I'm going to drop this over to the y-axis, right? And I now have that on the y-axis, so it's going to be r sine theta sine phi. Does everyone see that? I hope I haven't lost anybody. Remember, theta, it almost looks like a happy face, is positive from the z-axis downward. So it's going through 180 degrees, but it's going through those off the positive z-axis. All right. And then z, what is z then? Well, z would just be this distance right here, wouldn't it? And if we know that this over here, that's r, and then I drop it down here, that's r sine theta, well, then wouldn't this distance here be the same as this distance here, which would be r cosine theta? R cosine theta. They're probably thinking, well, that's pretty good, but what if I have to go the other way? What if instead of spherical to Cartesian, I have to go Cartesian to spherical, right? Cartesian to spherical. Well, if I'm going from Cartesian to spherical, that r, right? Because it works in 3 dimensions. Pythagoras' theorem works in 3 dimensions as well as it works in 2 dimensions, right? Is just going to be x squared plus y squared plus z squared, all taken to the square root. And that's r. And phi, if we think about phi from cylindrical coordinates, there's no difference here. It's still the inverse tangent of y over x, right? The harder one is theta. What is theta? Well, if we look at theta, we know the cosine of theta equals, well, let's look at the cosine of theta. Doesn't that equal z over the hypotenuse? Z cosine of theta is z over the hypotenuse, which is r. So if that's the cosine of theta, let me write that down here. Cosine of theta equals this right here, right? That's the distance right here, z over r. So the cosine of theta equals z over r. So theta then equals the inverse cosine of z over r. So that would be z divided by r, and we know that r is the square root of x squared plus y squared plus z squared, right? So there you go. That would be the transformation from Cartesian coordinates to spherical coordinates. Yeah, I'm sorry about that. What was I thinking? You know, I should have realized anyway. Well, that's obviously a shorter lecture, and I'm going to put up here coordinate transformations So now you should be able to transform between any of the three coordinate systems, and you should understand coordinate transformation equations. All right. And so now, just like with cylindrical Cartesian, we've come up with differential surfaces, differential volumes. We could use those later if we're going to integrate and stuff. So we may have to do that. And down here, we've gone through all of the transformations. Cartesian cylindrical, cylindrical Cartesian, spherical Cartesian, spherical or Cartesian spherical. You're probably thinking, hey, you've left off spherical to cylindrical and cylindrical to spherical. I will leave those up to you. And this is sort of a little shorter one than usual, but that's because I screwed up on that thing and I went back and I wanted to fix it all up. So I've actually done this lecture twice. Well, let's say 1.5 times. Okay. There are a couple other things I could bring up, but I really have no room left on that sheet, so we'll handle them with the next lecture. All right. Oops.